let's go ahead and begin. We finished sections 2.1, 2.2, and I sent you all this stuff out. 2.3 is going to be covered at the beginning of chapter 5. So we're not going to do that today. We're going to do section 2.4, and then the last one we have to do on Wednesday is 2.5, transformation. That's going to be the most time-consuming one. So we're going to push that off just to Wednesday. So today, all we're doing is symmetry. When we talk about if you guys want to close the door, go ahead. When we talk about symmetry, what does it mean to be symmetric? Yeah, it's like a mirror image, a reflection. For example, if I had a point 4,2, then another point for -2, what are those 2 points reflected across? Are you sure the y-axis? Yes, the x-axis. Because if you graph those 2 points, the only thing changes is the y. These 2 points are an example of this function. Cross the x-axis. What we say it's symmetric with respect to the x-axis. Another way we could say that is symmetric WRT the x-axis. W with respect to, just abbreviate it. Or we can say symmetric about the x-axis. So these are 3 different ways we can say the same thing. It's just choose one you like better. You can write WRT instead of writing with respect to, or you can just move symmetric about. Okay, so that's the first one. What if I had the point 2, 4 and -2, 4? That one is across the y-axis. So it's symmetric about the y-axis. Because the only thing that changes is the x value. And the last one, well, this example here would come from this function. Then the last one, 3 negative radical 7 and -3 radical 7. or they're both the same type of functions. This one, both the x's change and the y's change. This is across the origin. These points are symmetric about the origin. So when it comes to symmetry, what do we notice changes? If it's across the x-axis, the y value changes signs. So we go x, y to x negative y. That's for across the x-axis. Across the y-axis, the x values change sign. xy to negative x, y. And across the origin, both x and y change signs. xy to negative x, negative y. So far, so good? So if the values, depending on which values change, if it's the x's, then it's across the y value axis. If the y's change, it's across the x-axis. Let's look at some examples. All right. Y equals x squared plus 3. Let's test all three axis transformations. X-axis, y-axis, and origin. So what we're looking for is this. Once we do a change x, there's the signs of a variable. If it gives us the same answer as original, then that's where it's symmetric about. So let's see about the x-axis. What do we change for the x-axis? The y values. So we change from y equals x squared plus 3 to negative y equals x squared plus 3. Since there's a negative in front of here, change is this the same as this? I mean, even if we took out the negative, there's still that negative there, so it's not the same. So it's not symmetric about the x-axis. How about the y-axis? Y equals x squared plus 3. Here, we change x from positive x to negative x. Negative x squared is the same as x squared. The square gets cancels out the negative. So this equation looks like this. So this one is. And let's check out the origin. In the origin, we have to change both the y and the x. Change our signs. Negative x squared is x squared. Change all the signs. They're not the same. So it's not symmetric about the origin. All right. How about this one? Let's check across the x-axis, the y-axis, and the origin. See if it's symmetric about any of those. Squared plus y squared equals 4. X squared plus y squared equals 4. So for the x-axis, we change y. The y-axis, we change x and change both. So x squared plus negative y squared equals 4. Negative y squared is the same thing as y squared. So this looks like this. So it's symmetric about the x-axis. Try the y-axis now. Change x from positive x to negative x. Negative x squared is x squared. They look the same. So it's across the y-axis also. And cross origin, change both of them. So negative x squared is the same thing as x squared. Negative y squared, same thing as y squared. So it's across the origin also. Why is it symmetric about all three of those? It's very good. Radius what? Center where? Where's the center and what's the radius? Very good. Radius. Right, 2. Because it's all, this is r squared. This is square root. Very good, though. This is an equation of a circle. Okay, so that's symmetry we're looking at. Next thing we're going to talk about are odd and even functions. And then we'll see something odd and even functions, how they relate to origin and the y-axis. You know, it's easier if you want to. You can always log onto these computers and go to the Zoom at your computer so you can see it better here, closer. Odd versus even functions. A function is even if you change x with negative x, you get the same function. So you start off with f of x, and all you do is change x, you get the same thing. That's an even function. Have we seen something like this already? Where? Today. Very good. Excellent. Yes. An even function is symmetric about the y-axis. And you'll see this is a lot easier than what we've been doing. An odd function. A function is odd if you change x values and it changes the y values. So if I put a negative x in my function, it makes the entire function negative. Okay, this is the formal way of defining it. And this is what I told you, this way is a lot easier than changing the signs and everything. An even function, this is the easiest way of doing it. If all exponents are even, plus or minus if you have a constant. Number. So if all your exponents in your entire equation are all even, it's an even function. If all of them are even and you have a constant number, then it's an even function. odd. No constant. If all your exponents are odd and you have no constants. Let's see why this is. Here's the first example. So the way you test it, change x to negative x. Any even exponent cancels out the negatives. Negative 2 squared is negative 2 times negative 2, which becomes a positive 4, which is the same thing as 2 squared. So negative x to the fourth is the same thing as x to the fourth. Negative x squared is the same thing as x squared. So if you change x to negative x and you end up with the same question you started off with, that's even function. Is this one odd or even? Let's check it out. All the exponents are even and you have a constant. So if I change the signs, change the x's from positive to negative, the negatives get canceled by the even exponents. So those are both even. These are both even. Let's look at some examples of odd ones now. X to the fifth minus x, let's make it plus x cubed. First thing to do is change the sign of x. The negative to a fifth root is still going to give us a negative answer. Same thing here. So it's a negative x cubed. There's a plus sign and a minus sign. There's x to the fifth. Positive times negative is a negative. X to the third. Since both of these are negatives, so we can factor out a negative sign. That means that whatever is left in, change the signs. From a negative 5 becomes a positive, from a negative becomes a positive. So if you look at this is your original equation, but it's negative. It made the function negative, which makes it odd. This part is still there. The signs are different. This one's positive. This one's negative. Remember, to be odd, if you change the sign of X, it changes the function. Okay, show me, work that one out. Tell me if it's odd or even or neither. First thing we do is change the sign of X. X to the fourth plus negative X to the third. It has a odd exponent, so it stays negative. Even exponent gets rid of that one, so it becomes a positive 4x. That one becomes a negative. If we take out the negative, we get a positive x to the fifth minus x to the fourth plus x cubed. Does this look like this? Because of the negative sign here. So it's neither. It's neither odd nor even. And the last one. Y equals x to the fifth plus x to the third plus 3. Change x. Negative x to the third. So it becomes negative x to the fifth. Negative x to the third plus 3. Factor out the negative. X to the fifth plus x to the third minus 3. They're not equal, so it's neither. Okay, so let's recap those last 5 examples I did. And let's look for a pattern. Are we finished catching up? In this first one, we only had even exponents. If all of the exponents are even, then it's an even function. If all the exponents are even and you have a constant, it's still even. odd exponents. Nothing else? Odd exponents? The function is odd. If you have a mixture of odd and even, neither. Or if you have odds with a constant, it's neither. Whoops. So the only functions that can have constants are even functions. You cannot mix odds and evens. Other than that, it's just looking at them. You don't have to do any work. And we know if a function is odd, what is it symmetric about? Remember, in an odd function, x changes from positive to negative, and the y's change from positive to negative. So an odd function is symmetric about what? So odd functions are symmetric about the origin. So all you have to do is look at a function. Is if they only have odd exponents, you know it's symmetric about the origin automatically. And even exponents, I mean, even functions are symmetric about the what? Because here we changed x to negative x and got the same answer. The y-axis, right? So if the x's change and the y stay the same, then it's symmetric about the y-axis. Is everybody okay about the symmetry? I mean, symmetry about the axis, what it really means? Let me show you. If I had a graph and I have a point at -3, 5 or -3, 4. Give me a point that's symmetric about the y-axis. If I have a point -3, 4, give me the point that's symmetric about the y-axis. So if it's symmetric about the y-axis, you just change the x value from positive to negative, negative to positive. So it would be here. It would be at +3, 4. That's symmetric about the y-axis. Symmetric about the x-axis. Where would that point be? What's that? Very good. Because here's the x-axis, so we got to flip this way. So instead of -3, -4, it's -3, -4. You change the y's. And what would it be across the origin? Yeah, so it used to be -3, 4. It's going to be 3, -4. This is across the origin. See, this kind of stuff we need to know when changing points, the dimensions of points and signs, because the last section of this chapter, transformations, I'm going to give you a graph and I'm going to ask you to transform it, whether it's a horizontal shift, vertical shift, expansion, constriction, shrinking. There's a whole bunch of things you have to know. And that's why I want to say that to Wednesday. Okay, let's look at the homework assignments. How about this one? This is 2.4, number 1, homework. Determine the symmetry of this graph. Is it symmetric about both of them, X and Y? If you fold it with the X axis, does it look the same? No. So it's not A. How about B? So if you fold across the Y axis, they look the same. That's symmetric about the Y axis. So it is B. C? No. Origin? No. So the answer is B. How about this one? Is it symmetric across the X axis? Yes. Because if you fold it across the X axis, then you get the same graph. Determine whether the graph is symmetric with respect to the X, Y, and origin. So we have, it's question number 3. 6x minus 6y equals 0. So let's try x-axis first. Is this symmetric about the x-axis? We have 6x minus 6y equals 0. What do you change when you test for the x-axis? What do you change when you test across the x-axis? The y's, yeah. So we have 6, change that to negative y. So that becomes a positive 6y. So I've noticed the signs are different. Not symmetric about the x-axis. How about the y-axis? 6x minus 6y equals 0. For the y-axis, we change the x's. Okay, testing. Yeah, now they should hear me. I don't know. I'm gonna take these back. I just bought these this weekend. They suck. They don't work. Sorry about that. Okay, the next function. Determine the symmetries. This is 2.4, number 5. 4x to the fourth plus 7 equals y squared. Test the symmetries. We have x-axis, y-axis, and the origin. So 4x to the fourth plus 7 equals y squared. So the x-axis, I change the y. See what happens here. Negative y squared is same thing as y squared. They look the same. They're the same. So they're symmetric with the x-axis. 4x to the fourth plus 7 equals y squared. For the y-axis, we change x. So y squared. Negative x to the fourth is same as x to the fourth plus 7 equals y squared. They are the same, so it's symmetric with the y-axis. And the origin, change both x and y. If it's an even exponent, it cancels out the negative. So that becomes y squared. And they're the same. So they're symmetric about all three. So basically, here's a shortcut. Whenever you have a negative inside of parentheses to an even exponent, the negative's gone. If you have a negative to an odd exponent, it makes the equation, that value, negative. So this is pretty important to follow. All right. Determine the symmetries here. This one, 2, 4, 6, 5, y cubed equals 2x cubed plus 3. Test the symmetries. We have the x-axis, the y-axis, and the origin. For the x-axis, we change the y. So change the y to negative y. 2x cubed plus 3. It's an odd exponent, so it makes that part negative. Since change all the signs, We get 5y cubed equals negative 2x cubed minus 3. If we take out the negative, we have so, but it's not the same answer. It's a different sign, different answers. So it's not symmetric about the x-axis. Why is it not? Because it's an odd exponent. Same thing with the x for the y-axis. Since the x is an odd exponent, we know that one's not going to fail because it's going to change the sign of that. Five y cubed, 2x cubed plus 3. So I change the x to negative x cubed plus 3. This negative goes out in front, 2x cubed plus 3. Not the same, so it's not going to work. For the origin, you have to change both. We change the first one to a negative y, the second one to a negative x. So it becomes negative 5y cubed equals negative 2x cubed plus 3. Change the signs. 2x cubed minus 3. Not matching. How do we know by looking at the exponents and the numbers that it wasn't going to work on the origin? Remember, if you have odd exponents, can you have a constant? Nope. So that's how we knew it wasn't going to work. Because the only way you can have a function that's symmetric about the origin is if it's an odd function. An odd function cannot have a constant. Okay. Again, if you remember your library of functions, this one makes a lot of sense. That's 2, 4, 7. This one is x times y equals 2. Let's try across the x-axis, the y-axis, and the origin. xy equals 2. That's the same for all of them. That's the original one. So for the x-axis, I got to change the y to negative y. That becomes negative xy equals 2. Not the same, so no. For the y-axis, got to change the x. There's negative xy equals 2. Again, not the same. negative x. Negative negative is positive. They're the same, so it works. So it's symmetric about the origin. Now, is there another way we could have done that without having to do all this math? Right. Let's take this function and solve for y. Divide both sides by x. So y equals 2 over x. Does that look like one of the library functions? How about this one? 2 times 1 over x. Are either of those library of functions? One over x, what does that graph look like? Looks like that. Is this symmetric about the x-axis? No. Is it symmetric about the y-axis? No. How about the origin? Yes. We could have, just by seeing this equation here, no math being done, we could determine what those symmetries would look like. So yes, it's symmetric about the origin. All right. Find the point that is symmetric to the point 2, -5. It's 2, 4, 8. 2, -5. X-axis, y-axis, origin. So like we just worked on all these. What do we do to test x-axis symmetry? So we change what though? Change the y value, yeah. So since we started off at 2, -5, the point symmetric about the x-axis is 2, +5. So for the x-axis, you just change the y's. So for the y-axis, what do you change? The x values. So it becomes from 2 to -2. Leave the y alone. And across the origin, change them both. Change y, change x, change both. So far, so good. Find a point that's symmetric. Now, before I write this down, you should be done already. X-axis, Y-axis, origin. Our original point is -11, -2. What's this one going to be? Across the x-axis, what's the answer? -11, 2. Just change the y. The y-axis. Just change the x. The origin, change them both. Is this function odd, even, or neither? Okay, we have a guess of neither. How do we know if a function is odd? It's symmetric about the what axis? The origin. Is that symmetric with the origin? No. How about even? What's it symmetric to? Is this symmetric with the y-axis? Yes. So this is an even function. It's symmetric about the y-axis. Or this side of the graph looks like this side of the graph. It's across the y-axis. How about this one? Is this one odd, even, or neither? Why? One more time. Well, if you look at these, look at this point here. It's at 1, -2. -1, 2. That's changing x and y, isn't it? So the answer is no, but not for that reason. For this reason, because notice this is a solid point, this is an open dot. Every point has to be similar. I mean, it has to have change of signs. But since you can't use this point at -4, it doesn't map to +4. That's the only reason. Other than that, it would have been a symmetric about the origin picture. Because all I did was change the signs of the numbers, and that's what that did. So that one's neither odd nor even because of that one point. Looking at this, is it odd, even, or neither? Why? All the exponents are odd, and there's no constant. So it's an odd function. How about this one? Even. All the exponents are even, and there's a constant. Constants can only go with even functions. If the exponents are all even, or if they're all even and you have a constant, that's why I have a plus or minus constant. You can have it or you don't need it. So even functions can be all even exponents or all even exponents and a constant. How about this one? Odd, even, or neither? Yeah. Well, yeah, because 9 is odd. So it's odd. I know. This one here makes you start thinking because it's too simple. It's got to be a trick to it. Nope, that was it. That's it for 2.4. On Wednesday, we're going to do transformations, which requires a lot. We're going to look at moving functions vertically, horizontally, spreading them wider. Oops. We're going to vertically, horizontally, spreading them, shrinking them, stretching them out, up and down, and then pushing them down. We'll look at all of these possibilities on Wednesday. So you're getting to it. Like we just did the odd even functions. You did that just by looking at the equations. We're starting to build up our repertoire, and that if I just give you a function, you can tell me a lot more than that. Does it open up? Does it open down? Is it, how many intercepts can it have? What are the endpoints doing? Are they going same direction, different directions? That's what I'm trying to get you all to get to, but you have to memorize those tables first. And unfortunately, my earlier class had enough time that we did the quiz. We'll start off next time doing the quiz. This, that library function chart I gave you, memorize the pictures and the functions. Be able to go both directions. If I gave you a function, what picture does it match to? If I give you a picture, what function? Because that's going to help us in the next couple of chapters. All right, any questions? All righty then. I'm going to release you